Okay, students. Unit 4 Hydrogen. Unit 4 Hydrogen. In this session, I am going to teach the preparation of hydrogen, deuterium and tritium. Next, the properties of hydrogen, deuterium and tritium. Okay, so the next, the uses of hydrogen. Uses of hydrogen. Okay, the first one is preparation of hydrogen. Preparation of hydrogen. Already you know that in previous class, industrial laboratory preparation and electrical methods, electrolysis methods. So in this session, industrial productions, the preparation of hydrogen in industrial productions. The large scale hydrogen is produced by the steam reforming method. The steam reforming of hydrocarbons. The steam reforming. The steam reforming of hydrocarbon. Steam reforming of hydrocarbons. Okay, so example in hydrocarbon, methane. So methane mixed with steam. Methane mixed with steam and passed over nickel catalyst. Methane, so mixed with steam and passed over nickel catalyst. The temperature range 800 degrees Celsius to 900 degrees Celsius and 35 atmospheric pressure. The mixture of methane and steam is converted into carbon monoxide and hydrogen. Carbon monoxide and hydrogen. Right? So in reactant side, one carbon. In product side, one carbon. In reactant side, one oxygen, and product side, one oxygen. But in reactant side, 6 hydrogen. In product side, 2 hydrogen. So 3. Are you right? So CH4, methane. So steam reforming of hydrocarbons. Methane mixed with steam passed over a nickel catalyst. The temperature range 800 degrees Celsius to 900 degrees Celsius and 35 atm pressures. Okay, so the product carbon monoxide and hydrogen. In another method, in another process, the steam. The steam passed over a red hot coke. Red hot passed over a red hot coke. The steam is passed over a red hot coke to produce the carbon monoxide and hydrogen at 1000 degrees Celsius. At 1000 degrees Celsius, in another process, the steam passed over a red hot coke. Red hot coke produced carbon monoxide and hydrogen. Okay, so one carbon, one oxygen, 2 hydrogen, 2 hydrogen. So balance the equation at 1000 degrees Celsius. The mixed carbon monoxide and hydrogen gases in this way is called water gas. The mixture of carbon monoxide and hydrogen is called water gas, or also known syngas. Syngas. Syn means synthetic. Syn means synthetic. Right? Water gas or syngas. Syn means synthetic. Synthetic gas. It is used in the preparation of organic compounds. So, the preparation of organic compound, so the mixture of CO and H2 are called synthetic waste. The synthesis of organic compounds such as methanol and methane, etc. Example, the preparation of methanol from water gas or syngas. So, carbon monoxide and hydrogen. The mixture of water gas or syngas passed over a copper catalyst to give methanol. To write in reactant side 1 carbon, product side 1 carbon, reactant side 1 oxygen, in product side 1 oxygen. In reactant side 2 hydrogen, but product side 4 hydrogen. Okay, so 2 hydrogen, 4 hydrogen, so 2. CO, 2H2, CH3OH. You write? So, the mixture of carbon monoxide and hydrogens are called syngas or water gas. In another one example, the carbon monoxide reacts with the hydrogen to give simple hydrocarbon methane. You write? So see, 1 carbon and water. H2O, water. So 1 carbon, oxygen, 1 oxygen, hydrogen in product side 6 hydrogen. So 3H2. Right? So the mixture of carbon monoxide and hydrogens are called water gas, are also known syngas or synthetic gas. It is used in the synthesis of organic compounds such as methanol and simple hydrocarbon. Okay students, in the above two methods, the preparation of the mixture of carbon monoxide and hydrogens. But want to separate hydrogen gas. So to separate carbon monoxide and hydrogen gas. The next method, the conversion of carbon monoxide in water gas to carbon dioxide. The conversion of carbon monoxide in water gas to carbon dioxide. The excess of steam mixed with water gas, the mixture of carbon monoxide and hydrogen, water gas. The excess of steam mixed with water gas at 400 degrees Celsius passed over a shift converter. Contain the catalyst of copper or iron. Copper bar iron catalyst. Are you right? The excess of steam mixed with the water gas at 400 degrees Celsius. Okay, so passed over a shift converter contain copper bar iron catalyst to produce carbon monoxide and hydrogen. To produce the carbon monoxide and hydrogen. Right? Carbon monoxide and hydrogen. Right? 1 carbon in reactant side, so 1 carbon in product side. So 2 oxygen in reactant side, 2 oxygen in product side, 2 hydrogen. In the above process, the carbon dioxide is produced. The carbon dioxide is used in the solution of potassium carbonate. The solution of potassium carbonate. Okay, so use the solution of potassium carbonate to observe carbon dioxide gas. The hydrogen gas is separated. You write the carbon dioxide reacts with the potassium carbonate solution. Potassium carbonate solution. You write is converted into potassium bicarbonate salt. KHCO3. Potassium bicarbonate salt. You write so one carbon. So reactant side 2 carbon, but 1 carbon, so 2. So 2 carbon, oxygen 3, 2, 5, 1, 6, 3 into 2, 6. Potassium 2 potassium, hydrogen 2 hydrogen. Okay, so it's a separate hydrogen gas in this method. You write? So in this reaction is called water gas shift reaction. Water gas shift reaction. Right? Okay, students. The next one is preparation of deuterium. The preparation of deuterium. Okay. The electrolysis of heavy water. The electrolysis of heavy water D2O. Heavy water D2O. Right? The natural water. The natural water H2O, protein water, contain 1.6 into 10 power minus 4 percentage of D2. A normal water H2O contain 1.6 into 10 power minus 4 percentage of D2O. Okay, so the 20 liter of normal water contain 1 milliliter of heavy water. 1 milliliter of heavy water. 1 by 6,000. So 1 D2O per 6,000 normal protein water. Right? So normally the dissociation of protein water is much more than heavy water. In electrolysis process, the dissociation of protein water is much more than heavy water. When the electrolysis of normal water, in electrolysis of normal water, the liberation of hydrogen is much more faster than D2. The liberation of hydrogen is much more faster than D2. Right? So the electrolysis is continue to reach the enriched amount of D2O. So the further electrolysis with the D2O, the further electrolysis of D2O, heavy water gives deuterium. And oxygen. Right? How many oxygen? 1 oxygen. In product side 2 oxygen. In reactant side 1 oxygen. So 2. In product side 2 oxygen, but reaction side 1 oxygen. So 2. How many deuterium? 4. So 4. Right? So the preparation of deuterium in electrolysis of heavy water. Electrolysis of heavy water. You right? The next preparation, the preparation of tritium. The preparation of tritium. Already you know that the trace amount of tritium present in the atmospheric gas. Atmospheric hydrogen gas, the trace amount of tritium is present. So the tritium is prepared from artificially the bombarding lithium. The bombarding lithium with slow neutron. In the nuclear fission reactor. Right? So lithium 3,6 bombard with neutron 0,1 to give helium 2,4 plus tritium 3,1,3. Right? So in a nuclear reactions, in both sides balance number of atomic number and mass number. In both sides balance atomic number and mass number also. You right? The atomic number 3, so 2 plus 1, 3. Mass number 7, 4 plus 3, 7. It's an artificial preparation, nuclear fission reaction. So lithium is bombarded with neutron. The bombarding lithium with a neutron to give tritium and helium. So okay students, the properties of hydrogen. The first one is physical properties. The hydrogen is colorless and odorless, tasteless and lightest and highly flammable gas. Hydrogen is a colorless, odorless and tasteless and lightest and highly flammable gas. The hydrogen is a non-polar diatomic molecules. Okay, so covalent bonded with the same electronegativity contain hydrogen atom. Okay, so non-polar covalent bond. So non-polar covalent bond occur between the two hydrogen atoms. But in hydrogen and chlorine, the two different electronegativity elements. The chlorine is a highly electronegativity than hydrogen, so attract the electron towards itself, so negative. In positive, it's a polar diatomic molecules. So polar diatomic molecules, but hydrogen is a non-polar diatomic molecules. The hydrogen, it can be liquefied under low temperature and high pressure. So hydrogen acts as a good reducing agent. So reduce some organic compounds such as aldehyde, carboxylic acid and unsaturated compounds. For example, acetaldehyde CH3 CH double bond O. Acetaldehyde reacts with the hydrogen in presence of nickel catalyst to give alcohol CH3 CH2OH methanol. It's a reducing reaction. So act as a reducing agent. Hydrogen acts as a reducing agent. Right? So the next chemical properties of hydrogen. The first one is action with oxygen. Action with oxygen. Right? Hydrogen reacts with oxygen to give water. This reaction is explosive reaction. Say exothermic reactions, more energy is released. Exothermic reactions, so more energy is released. 2 oxygen, 2 and 2. Right? It is used in fuel cells. Fuel cells to generate electricity. You right? The next, action with the halogen. Action with the halogens. Fluorine, chlorine, bromine, iodine. The reactivity series, the fluorine is highly reactive than chlorine, bromine and iodine. Okay, the hydrogen reacts with the fluorine in dark condition also. Okay, so highly reactive fluorine hydrogen reaction is a highly reactive reaction. So this reaction occur in dark condition are also say explosive reaction to give hydrogen fluoride. You right? The next, hydrogen reacts with chlorine at room temperature or sunlight. Okay, so room temperature or light to give hydrogen chloride to HCl. Hydrogen chloride. Next, hydrogen reacts with bromine at the high temperature. The reactivity series decreases. The reaction of halogens. The action with the halogens. Okay, the hydrogen reacts with the halogen tendency to decreases. Okay, H2, Br2, and high temperature to give hydrogen bromide. But hydrogen rarely reacts with iodine. Presence of photoelectric effect. Right? So photosynthesis process. Right? To give hydrogen iodide. The order of reactivity series, fluorine is higher than chlorine, then bromine and iodine. Right? The third one is the action with the metals. So third one is the action with the metals. The lithium reacts with the hydrogen to give lithium hydride. So 2 hydrogen, 2. Then sodium reacts with the hydrogen to give sodium hydride. So 2. In these 2 reaction, the hydrogen oxidation state is H+. Hydrogen oxidation state is H+. Hydrogen is H+. But in this reaction, it's a metal hydride, lithium hydride, sodium hydride. The oxidation of hydrogen -1 oxidation, metal plus oxidation. So hydrogen is a negative oxidation state. Okay, so electronegativity of hydrogen is more than metal. Right? This metal hydride act as a reducing agent. Yes, metal hydride act as a reducing agent. Reducing agent in synthetic organic chemistry. Okay, the metal hydrides are used reducing agent in synthetic organic chemistry. Thus, metal hydrides are used to prepare other reducing agents like lithium aluminum hydride, and sodium borohydride. Lithium aluminum hydride and sodium borohydride. You write the preparation of lithium aluminum hydride and sodium borohydride from metal hydride. Okay. The lithium hydride reacts with the aluminum chloride. Reacts with the aluminum chloride to give lithium aluminum hydride. Lithium aluminum hydride and lithium chloride. Lithium chloride. So lithium is more reactive than aluminum. Okay. So lithium aluminum chloride and lithium chloride. So balance the reaction. How many hydrogen? 4 hydrogen. 4 hydrogen. How many aluminum? 1 aluminum. But how many lithium in reaction side? 4 lithium. Already 1. So 3. Fluorine are also 3. Okay, balance the reaction. So it's a good reducing agent. Lithium aluminum hydride. Lithium aluminum hydride. Lithium aluminum hydride. Okay, so next preparation. Sodium hydride. Sodium hydride reacts with trimethyl borate. Organoboron compounds. Organoboron compounds. Trimethyl borate. Trimethyl borate. Organoboron compounds are trimethoxyboron. Trimethoxyboron. So to give sodium borohydride. Sodium borohydride and sodium methoxide. Sodium methoxide. Right? Okay. So how many hydrogen? 4 hydrogen. How many hydrogen? 4 hydrogen. You write? So 4. How many sodium? 4 sodium. Already 1. So boron 1. Already 1 sodium. So 3. Okay, so same balance. Okay, 4, 4, 1, 1, 1, 1, 3, 3. So sodium borohydride. Sodium borohydride and sodium methoxide. Sodium methoxide. You write the fourth one, action with the fourth one, act as a reducing agent. Act as a reducing agent. Okay, the unsaturated hydrocarbon is converted into saturated hydrocarbon. For example, CH triple bond CH, ethane, it's alkyne. Okay, in presence of nickel bar hydrogen. Hydrogen act as a reducing agent. They break the weak pi bond. Weak pi bond is converted into CH2 double bond CH2, ethylene, alkyne, alkene. Then further reduced alkyne to alkane, converted into alkane. So nickel bar hydrogen. So another one pi bond is break. So to give CH3 bond CH3. It's a saturated hydrocarbon. Saturated hydrocarbon. The unsaturated hydrocarbon is converted into saturated carbon by using hydrogen. This process is called reducing process. They react as a reducing agent in hydrogen. Okay, students. The next one is properties of deuterium. Properties of deuterium. The chemical properties of deuterium. The first one is action with the oxygen. Action with the oxygens like hydrogen. The deuterium also reacts with the oxygen to give deuterium oxide. Deuterium oxide are also called heavy water. Heavy water. You write the D2 reacts with the oxygen to give D2O. D2O. Two oxygen 2 and 2. So deuterium oxide are also called heavy water. Heavy water. The second one is the action with the halogen. Action with the halogens. Halogens. The deuterium react with all halogens to give deuterium halides. Deuterium halides like hydrogens, right? Hydrogens. Okay. So in general equation, D2 reacts with all halogens to give deuterium halide. Deuterium halide. Right? So 2. For example, fluorine. So D2 plus F2 will give D2 plus F2 will give DF, deuterium fluoride. Okay, 2. So deuterium fluoride. Okay, so already balanced in this reaction. D2X2, 2 times D, 2 times halogens. Okay, so X is equal to fluorine, chlorine, bromine and iodine. Okay, the third one is the deuterium exchange reaction. Deuterium exchange reaction. The deuterium exchange reaction. Deuterium exchange reaction. Okay, so the deuterium replace the reversibly hydrogen. The deuterium replace the reversibly hydrogen in compounds. Hydrogen in compounds, either partially or completely. Partially or completely. Depends upon the reaction condition. Depends upon the reaction condition. For example, methane, CH4, methane. Methane reacts with deuterium D2 to give deuterated methane D4. Deuterated methane and liberate hydrogen H2. Okay, so 4 hydrogen to 4 neutron, so 2. Okay, so deuterated methane. Deuterated methane. And next one is ammonia, NH3, ammonia reacts with deuterium, right, to give the deuterated ammonia, right, N-D3 plus liberate hydrogen H2. Okay, so R number, even number, right? So R number, even number. To change R number 3 in even number. Okay, so 6 deuterium. So 2 nitrogen, 6 hydrogen, 6. Deuterated ammonia. So deuterium exchange reaction. Okay, the next one is the chemical properties of tritium. The chemical properties of tritium. Already you know that the tritium is a isotope, radioactive isotopes. Okay, so radioactive isotope tritium. So emit the beta particles, auto-dissociation processes occurs. So radioactive compound, so self-dissociation is occurs. Auto-dissociation is occurs. So T₁ Okay, so automatically dissociated to give helium isotope plus tritium. So emit electron, emit the beta particles, beta E -1 0 electron, beta particles. You write 3 3 1, 2 minus 1 1. Okay, so in both sides balance the atomic number and mass number are also in radioactivity reactions, nuclear reaction. So in reactant side mass number 3, so product side are also mass number 3. In reactant side atomic number 1, so product side 2 minus 1 1 is the auto dissociation reactions. Automatically tritium emit helium and beta particles in half-life period, 12.3 years. 12.3 years. The half of the tritium decomposition time, half of the tritium decomposition time 12.3 years. 12.3 years. Okay, students. Next one is uses of hydrogen. 5 more question. Over 90% of hydrogen produced in industry is used for synthetic applications. One such process is Haber process, which is used to synthesize ammonia in large scales. Ammonia is used for manufacture of chemicals such as nitric acid, fertilizers and explosives. Okay, the Haber process, the atmospheric nitrogen and hydrogen reacts with give ammonia at 380 to 450 degrees Celsius at 200 atm, the catalyst used in iron. The second use is it can be used for manufacture the industrial solvent methanol from carbon monoxide using copper as catalyst. So, CO and H2 is a producer gas. CO and H2 is a water gas or syngas. Okay, the mixture of CO and H2 is a water gas or syngas passed over a copper catalyst to give methanol. The third use, the unsaturated fatty oils, CH2 double bond CH2 is a unsaturated fatty oils can be converted into saturated fats called vanaspati. The margarine is a synthetic butter by the reduction reaction with the platinum hydrogen. The presence of platinum catalyst H2 to give CH3 bond CH3, the saturated fats. The unsaturated fatty oils can be converted into saturated fats called vanaspati by the reduction reaction with the platinum hydrogen. The fourth uses in metallurgy. In metallurgy, hydrogen can be used to reduce many metal oxides to metals at high temperature. For example, the metal oxide cupric oxide is converted into copper by using reducing agent hydrogen. Okay, so CO and H2O and tungsten oxide okay, converted into tungsten by using reducing agent hydrogen. Right? The fifth one is the atomic hydrogen and oxyhydrogen. Atomic hydrogen and oxyhydrogen torches are used for cutting and welding. The sixth one is liquid hydrogen is used as a rocket fuel. The seventh one is the hydrogen is also used in fuel cells for generating electrical energy. The reversible uptake of hydrogen in metals is also attractive for rechargeable metal hydride battery. Okay, students, 5 more question, uses of hydrogen. Alright? Okay, students. Thank you, students. We'll meet next class.